Hi again, welcome to this video, the second of two, on the expected values of discrete random probability distributions. It elaborates on the main concepts of this part of probability and shows how to interpret the values contained in such distributions. The previous video described discrete random probability distributions as being presented as a table in which specified values of a variable being investigated, say x, are linked to the probabilities of those values occurring. Using those values for the variable and their probability, we can now estimate the expected value of the variable and the variability of the results around the expected value. We start with a table like those in the previous video. In this table, I'm counting the number of fish which pass a particular part of a stream every 30 seconds, and I'm showing the probability of that occurring. Notice that there is a chance of all 5 values occurring at random, and the sum of the probabilities is equal to 1. But the chance of 2 fish passing is higher than any other single number. Further, the chance of more than 2 fish passing the point is greater than the chance of less 2 fish passing the point. So there must be some environmental goodness going on there. As probabilities are generally based on a population, here the number of fish in the stream, we refer to the population mean, or the average, and we give the Greek symbol mu to this, as the expected value of the characteristic we are analysing. In other words, the expected number of fish passing that particular point. The expected value is generally written as E followed by the name of the variable, x or fish. Hence, the expected value of x is the population mean. To calculate the expected value, we treat the distribution in the table like a frequency distribution, in that we calculate a weighted sum of the values. The weights are, of course, the probabilities. So we calculate mu by multiplying the number in the top row by the number underneath it. So 0 times 0.05 plus 1 times 0.15 up to 4 times 0.2. We add all those together and we get 2.4, and this is our expected value for the number of fish passing that point in 30 seconds, so nearly 2.5 fish. So the expected value of x, ex, is not necessarily a value we might expect for the variable, because we can only have a whole number of fish going past. Instead, it is a weighted average. If the probabilities are based on samples, then the expected value is an estimate of the population mean. The strategy for calculating is exactly the same, however. The sample mean is given the symbol x, or the name of the variable, with a bar over the top of it. As more and or larger samples are added into the data bank, the probabilities become closer and closer to the real distribution values, and the sample mean then becomes closer and closer to the population mean. Different sets of data sampled from the population vary from one another. Hence, instead of just finding the expected value, it is also important to estimate the extent of the variability of values in a distribution. That estimate facilitates comparison between subgroups. To measure variability, just as with the basic descriptive statistics, we use a statistic called variance and its variant called standard deviation. The concept of variability is based on the difference between each observation and the expected value. In other words, x minus ex or x minus mu. In our table, the expected value is 2.4, so we may go 0 minus 2.4, which is minus 2.4, and then 1 minus 2.4, which is minus 1.4, and so on and so forth. As some values calculated from this calculation are negative, all difference values are squared to remove the minus sign. They're then added together, as they are all then positive, The value calculated for this computation is called the variance. That seems, and is, a hard or a long way to do the calculation. Now we all know that maths is meant to be easy, so try the following approach instead. So step 1. To the table you have already prepared, add another row below. In this new row, write the square of the corresponding number in row 1. So 0 in the top row goes to 0 squared, or 0 in the bottom row, and so on and so forth. The 3 in the top row goes to 3 squared in the bottom row, so 9, etc. Step 2. Multiply the new square value by the px value above it, and then add all of these values. So our sum is 0 in the bottom row times 0.05 in the one above it, plus 1 times 0.15, and so on. Add all these together, we get 7. Now, from this sum of 7, we're going to subtract the square of the expected value, which we have already calculated. So the variance is now going to be the 7 from step 2 minus the expected value of 2.4 all squared, and that gives us 1.24. So now our job is to smile, because that value we've just calculated is the variance. Now step 5, take the square root of the number we've just calculated to obtain the standard deviation. So the square root of 1.24 is 1.11, and that's our standard deviation value. Sometimes the question we're being asked may start with a frequency table. In this table here, we have a table summarising tossing 4 coins at once 160 times and counting the number of heads that are showing. So out of our 160 tosses, we had all tails, in other words no heads, 6 times. We had 2 heads, and therefore 2 tails, 56 times, and so on and so forth. We now calculate the relative frequency, and that is the frequency for each outcome divided by the number of trials, here 160. So 6 divided by 160 is 0.038. 45 divided by 160 is 0.281, and so forth. So these relative frequencies are now going to be used as the probabilities. The expected value, EH, or the number of heads, is going to be 0 in the first column times our relative frequencies, 0.038, plus 1 times 0.256, and so on and so forth, up to 4 times 0.075. Add all those together, our expected number of heads is now 2.1. To calculate the variance, we add another column. Previously we had a row, so we add another column with the square of the numbers from column 1 again. So our expected value for h squared is going to be 0 times 0 plus 1 times 0.256 plus 4 times 3.35, and so forth, linking column 4 to column 3. Add those together, we get 5.385, and then the variance is calculated by using that number, 5.385, and subtracting the 2.1 for the expected value all squared, which gives us 0.975. Taking the square root, the standard deviation is 0.99. Using sample values like we did for the coin tossing experiment, we are really calculating sample estimates for the population values of the mean, mu, and the standard deviation, sigma. So we're using a smaller number. The law of large numbers says that as we increase our sample size, we get closer to the actual values of the population parameters. We've got a convergence from our observed values all the way through to our population values. With the expected value, i.e. the mean, and the standard deviation known, we can apply concepts associated with the normal distribution to help our description of our discrete probability distribution, and we'll deal with that in the normal distribution section. So these are the main approaches you need to calculate expected values given a discrete random distribution. In the next probability videos, we review continuous probability distributions and then normal distributions. Go and do some test yourself one expected value questions on my website, drjaysmath.com. Hit the like button and subscribe if you haven't already, then you'll get notification about new videos. Good luck. See you in another one of my videos shortly.